I want to talk about the bipolar NPN transistor. The symbol for the NPN transistor is this. It has three terminals. The one with the arrow is called the emitter. This terminal is called the base. And this terminal is called the collector. How this transistor works is that you put in a small base current into the base, and you get a large current flowing from the collector to emitter. So small current in, big current out, it gives you a gain in current. So let's look at the structure of this device. It's composed of three regions. Let's say that this is the emitter region. It's an N-type material. The base region is a P-type material, and the collector region is an N-type material. So this is the base terminal. This is the emitter terminal, and this is the collector terminal. So what we have here is two back-to-back diodes. If we draw the diode configuration, we have a base emitter diode. This is the base, this is the emitter. And then we have another diode up here. That's the base to collector diode. This is the collector terminal. So what happens is we put a small current in the base into this diode. We get a large current flowing through the collector to emitter. So let's think about what's happening in this region. Now we know that the N material is predominantly, the predominant carriers are electrons. So when this base emitter diode is forward biased, we get a large amount of electrons that flow into this base region. And the electron tend to flow across to the collector region. Because this base region, the width of this base region, I'll call it W, is made very thin. So when the diode starts to conduct, an enormous amount of electrons will go into this base region from the emitter side, and they will diffuse over into the collector region. And so for a very small current in this direction, electron flow, we get a large current in this direction. So this is the flow of electrons, but engineers always think in terms of positive current. So when we think of current, we'll think of the current flowing into the base and from the collector to emitter, rather than the flow of the electrons, which is in the opposite direction. So if I plot the current versus voltage characteristics for this transistor, this axis will be voltage collector to emitter. This axis will be current in the collector. Now if I plot typical characteristic, let's say I put a little bit of base current in, and I plot this characteristic, I'll get 0 here. Then do something like this. There'll be a slight slope, and eventually the transistor will break down, and I'll get a huge current flowing. So an interesting thing to recall is that there's a slight slope to this curve. It's not perfectly flat. And what's happening is that as I increase the collector to emitter voltage, I'm reverse biasing this base to collector junction. When I do that, that increases the width of the depletion region for the base collector. And the increase in depletion width makes this base width a little smaller. And that actually improves the transistor performance a little bit. So that's not so harmful. Now if I have a little bit less base current, I'll get a curve that's further down here, and then eventually it breaks down. So there's an important characteristic, or an important parameter for this NPN transistor, and that's called beta. And beta is defined as the collector current divided by the base current. So it's a measure of the gain, of the current gain that the transistor can produce. And a typical value could be 100 or so. Let's do a very simple circuit design to illustrate how we can use this NPN transistor. Let's say I have a 5-volt power supply. I'll connect a resistor to a NPN transistor, and in the emitter circuit I'll put in another resistor to ground. And the voltage at the base I'll call V in. The voltage at the collector I'll call it V out, V0. And let's choose some resistor values. I'm going to choose 2 k ohms for the collector resistor and 1 k ohms for the emitter resistor. And I'm going to set V in at 1.7 volts. Now we know that this NPN transistor forms a diode from the base to the emitter terminal. And we know that the approximate forward drop in this base emitter diode is a rule of thumb about 0.7 volts. So I have 0.7 volts from this emitter to the base. And since I have 1.7 volts at the base, that tells me that my emitter voltage is 1 volt. And 1 volt and 1 K produces 1 milliamp of emitter current. So I have 1 milliamp flowing in the emitter. And I have a fairly high beta transistor. We'll say a beta of 100 or more. So better than 99% of this current is flowing in the collector terminal. So I'm going to round it to 1 milliamp. Now this 1 milliamp times 2K gives me 2 volts across the 2K resistor. So this V out is initially sitting at 3 volts. So what happens if I change the input voltage? Instead of 1.7, let's say I set it at 1.8 volts. So I go up 100 millivolts, or 1/10 of a volt, and I produce more current in this emitter. Now my current is 1.1 milliamp. And that current is essentially going to all flow in the collector. So I have 1.1 milliamp flowing through a 2K, which gives me an extra 200 millivolts. I give 100 millivolts in, and I'm getting a 200 millivolt change in V out. So my output voltage sits at 2.8 volts. So this circuit has provided a voltage gain. So I could write an equation for the change in voltage out is equal to in this case minus the change in the V in, times this ratio of resistors. I made a 2-to-1 ratio, collector resistor to emitter resistor. So if I make a general equation, I say this is the R in the collector divided by the resistor in the emitter. And so if I were to, instead of just changing this by 100 millivolts, let's say I put a sine wave into the input. So I cause the input voltage to do something like this. And we'll say that this is sitting at about 1.7 volts. So my output voltage, let me change colors here. The voltage at the output is inverted, but it changes twice as much. So I get an output voltage that looks something like this.